We'll start the application of exponential and log functions with growth and decay problems. So let's say y is a quantity whose rate of change with respect to time is proportional to the quantity that's present at any time. And we'll call the time t. Then y can be represented in this form, where y equals y naught e to the kt. Now y naught is the initial value, or the value when t equals 0. The value k is called the constant of proportionality, and we say exponential growth occurs when k is greater than 0, and exponential decay occurs when k is less than 0. And this exponential growth formula can be written other ways, and so a few ways you might write it is a equals a naught e to the kt, p equals p naught e to the kt, or y equals c times e to the kt, where c is some constant. And in finite math, we actually, with continuous compounding, you'll actually see this in the finance section, where we use a equals p times e to the kt, but instead of k in that formula we use the annual interest rate r. Okay, so we'll start with an example. So this first example, it's going to be a little bit easier for you because I'm actually going to give you the growth formula. So here it says the population of a certain city is given by this formula: a equals 5,000 e to the 0.001 t. So the initial population is given to be 5,000, and the growth constant here is 0.001, and since it's positive, that you know we have growth. Now a represents the population at time t, and t represents the time in years. So it says find the population at the end of 5 years. This is a pretty simple part to solve this. So to find the population at 5 years, you just evaluate the function when t is 5. So you get 5,000 times e to the 0.001 times 5. And that's the same as 5,000 times e to the 0.005. And using a calculator, I got the initial population. I've got not the initial population, but I got the population after 5 years is 5,025. Now, the second question says, how many years until the population doubles? Well, since this is the initial population, 5,000, if I want the population to double, I'm just going to set the population equal to 10,000, and then I'll solve this for the time so I can find the number of years it takes for it to double. So the first thing I would do here is just divide both sides of this equation by 5,000. If you divide the right-hand side by 5,000, that'll just cancel the 5,000. And if you divide the left-hand side by 5,000, 10,000 divided by 5,000 is simply 2. So you'll just get 2 equals e to the 0.001 t. And we learned in the last section that you can solve this by taking the log of both sides, and I'll just take the natural log of both sides. So take the natural log of 2, and then here I'm going to take the natural log of e to the 0.001 t. And if you'll remember, I told you in some cases it doesn't matter whether you use common log or natural log, but since this base is e, I'm going to use natural log, because I know if I take the natural log of e to some power, then that's just going to equal whatever the power is. So the natural log of e to the 0.001 t is simply 0.001 t, and then to solve this for t, just divide both sides by 0.001. So I'll get that t equals the natural log of 2 divided by 0.001, and so I got 693.15 years for that example. Now, as I said, in that problem you actually had the formula given, but sometimes you're not given the formula. So the guidelines for modeling an exponential growth and decay formula are these. First of all, use the given formula to write the given information, to write 2 sets of conditions. Now this usually includes an initial condition and a later condition. and then use the initial condition to actually solve for the constant. So the value when t equals 0 is the constant. And actually, since I'm actually telling you that when t equals 0, that's going to give you that constant a naught or c or p naught or whatever we're using for that particular variable. And then use the additional condition to solve for the other constant, the k, the constant of proportionality. And then use the completed model to answer further questions. Now, I don't want to get lost on talking about this, but I'll give you a minute to freeze the video and just read this paragraph here. So read that paragraph. You might find it interesting if you do search for a population clock. And so I'm going to go ahead and go on, but if you want to read that, just pause the video and read that. Okay, so now in this problem, I'm actually given two conditions. I'm given the initial population. In the year 1900, I'm given that the initial population is 12,500. And then I'm actually given another condition that 20 years later, the population grew to 16,000. Now, if we assume exponential growth, we can actually develop a exponential growth model for this. But really, I said earlier you need to solve for this constant, but actually you don't need to solve for it, because I'm already telling you that this constant here is just the initial population. So in this problem, the initial population is 12,500. So we know that the population formula would be P equals 12,500 e to the kt. Now, I want to solve for this rate of growth constant, k, so that's where I use the other condition. The other condition is that the population is 16,000 when t is 20. So let's plug 20 in here for t, and I'm going to put it to the left of the k. So I'll get 12,500 times e to the 20k, and I know that when t is 20, the population should be 16,000, so I'll put that in for p. Now, to solve for k, I can actually take this and divide both sides by 12,500. So if you divide the right-hand side by 12,500, it'll just cancel that. And if you divide the left-hand side by 12,500, just grab your calculator and do it, and you'll see 16,000 divided by 12,500 is actually 1.28. So that'll give me 1.28 equals e to the 20k, and then I can take the natural log of both sides. So I have the natural log of 1.28 is equal to the natural log of e to the 20k, and we know that when you take the natural log of e to the 20k, you just get 20k, and then to solve for k, divide both sides by divide both sides by 20, and you get the natural log of 1.28 divided by 20 for k. And actually right here I've got a slight typo here. I've got it correct in the formula, but there I don't have it correct. It should be 0.01234. Okay, so the solution there for k is 0.01234. So now I can go back up here to my model, and I can go ahead and put the k value that I found into the model, and I'll get that p equals 12,500 e to the 0.01234 times t. Now what this allows me to do, now that I have this completed model, I'm actually able to solve for p if you give me a particular t value, but I can also solve for t if I know a particular p value as well. So part B says use the model to predict the population for the year 1950. Now remember, we started at 1900, so that would be when t was 0 was 1900. So the year 1950 would mean that t is 50. So we'll just take this model and we'll replace t with 50, and we'll grab our calculator and calculate 12,500 times e to the power of 0.01234 times 50. And to the nearest whole number, I got 23,167 for the population. Now part C says estimate when the population will reach 37,500. Okay, so basically what I'm doing here is I'm asking you when will the population triple, because 37,500 is actually 3 times 12,500. But anyway, if you just put in 37,500 for P, then you're going to be solving for T this time. So you have 37,500 equals 12,500 e to the 0.01234 t. Now, again, like I did over here, you're going to divide both sides by 12,500, and if you divide the right-hand side by 12,500, it'll just cancel. And then if you divide this side by 12,500, you'll just get 3. So I'll get 3 equals e to 0.01234 t, and then I can solve this by taking logs. So take the natural log of both sides, and on the left I get the natural log of 3, and then when you take the natural log of e to this power, you just get that power, which is 0.01234 t. And then go ahead and just divide both sides by this 0.01234, and you'll get t equals the natural log of 3 divided by 0.01234. And that's a little over 89, so about 89 years. And so if you count 89 years past our initial time, that's going to give you the year 1989. And so that's how we solve population growth problems. Alright, let me go ahead and do this problem here. This is actually an example of decay. So the half-life of material is the amount of time it takes for half of the material to decompose. For example, if the half-life is 10 years, after 10 years half will remain. After 20 years half of half will remain, and so forth. So here you know the half-life of a radiomaterial is 20 years, and you have an initial amount of 80 kilograms to be disposed. And it says construct an exponential model that gives the amount of material remaining after t years, and how much of the material will remain after 200 years. So we're going to use the exponential model here that we've been using, and we're going to plug in 80 since 80 is our initial value. And since we know the half-life is 20, then we know the initial value will be cut in half. In other words, it'll go from 80 to 40 when t is 20. So I can go ahead and put 40 in for the amount and put 20 in here for t, and I'll get 40 equals 80 e to the 20k. Now, if you divide both sides by 80, you'll get 0.5 on the left and e to the 20k on the right, and then you can take natural log of both sides to solve this, and you'll get natural log of 0.5 equals 20k, and then just divide both sides by 20 to get k. So k would be the natural log of 0.5 over 20, which is negative 0.03466. And then the question says how much of the material will remain after 200 years. So all I have to do is take this completed model, 80 times e to the negative 0.03466 t, and replace t with 200. And then I grabbed my calculator and did that calculation, and I got that the answer was 0.078 kilograms. Now you might notice here that k was negative, and that is consistent with the fact that we know that the growth is decaying here. In other words, the function is decreasing. So anyway, theoretically it never all decays, and but our answer is 0.078 kilograms. Now I've got some other examples I want to show you, and so I'll show you some compound interest problems in the next video.